Hello everyone. In this video, I'd like to discuss how can we program a first-order model into PLC. In this video, I will use the Siemens TI Portal platform, and I will use the Siemens PLC as the platform to implement this equation. But actually, it doesn't matter which PLC you are using, because either we can use the ladder logic, or more common way, we will use structured test, or in Siemens we call it ICL, to program this equation. And the basic idea, if we quickly recall the previous video, firstly, we will have a first-order transfer function. In the first video, I explained how can we use the response curve, especially the bump test, the step response curve, to determine a first-order transfer function. Using the bump test step response curve, we can get this first-order transfer function. And to implement the S-domain transfer function into a computer system, into embedded system, or into PLC system, so I have to transfer this S-domain transfer function into Z-domain, and then ultimately transfer to difference equation, this style. And once we get this style, it will be very easy to use the computer system to implement the first-order model. So in the industry practice field, so this is the PLC is controlling a regulator and the heater system, and we are using the sensor transmitter as the temperature feedback. This controlled object is input is a voltage. So we temporarily use the voltage as the input, the unit for this heater system, and output, that's the temperature. And using the curve, we got this first order transfer function. To implement this transfer function into computer system, we have to involve the zero order holder, okay? And this is the previous video we discussed. You can review my previous videos. And after we involve this zero holder, then we can derive this equation into this style by using the first order transfer function. And ultimately, we got this difference equation like this. And then from the original first order transfer function, we can use this equation to program into our computer system or PLC system. And actually, this is very easy. So here, Y means the temperature, and X means the input of this regulator, the heater system. And in this case, I'm using the voltage as an input of here. Here we will see the only portion it looks complicated is this area, but actually that's easy, because once you have the first order transfer function, this expositional area is just a constant value, solid here. The A here, that means expositional frequency. And the TS, this is the sample time. And the sample time is up to you. If you are using 0.2 second, 200 milliseconds as the cyclic call to run this equation, then the TS is equal to 0.2 second. Here the unit is second. And xk minus 1, that means the one sample before the input signal. And yk minus 1, it also came from the one sample before the temperature feedback. Then we can use this equation to calculate your y. And once it's running into the computer PLC system, then this equation will do the recursive style. So it keeping looping here. And in this case, I will use the GS equal to S plus 0.1. 0.1. A here is equal to 0.1 times 50. This is basically a slow response, a temperature system, okay? And how this came from, you can review my previous videos. So I was using an example, temperature example. That time A was equal to 0.11. So too easy to calculate here, I will use 0.1. It's almost the same. And this is my GS transfer function here. And in the meantime, when I determine this equation, so that time, the initial status, I call that x00 equal to 1 volt. And the y00 was 50 degree. That means based on the 1 volt control signal, and once we regulate from 1 volt to 3 volt, then the y00 will based on the 50 degree, then do the first order style curve. And here, I like to explain one thing based on some question from the previous videos. Some people will ask, say, if now I give a 3 volts to this system, 1 hour or after 30 minutes, when the system gets a settling status, what the final temperature this system will be. So if you recall from the transfer function knowledge, when we give a system a step response, and the step response output is equal to Cs equal to Rs times Gs. So this response equation will equal to this. And then to calculate a step response, the settling value, so we'll use the limits. This is the limit when the time got infinite, that means S equal to approx to 0. And then came from this equation. This is S times Cs. Cs come from here. Then this equation will equal to 1S times S here and A as AK. So S here eliminate. And when the S approx to 0, so this equal to 0, then here this A over A equal to 1. Then ultimately when the system get a settling status, so the final will be the K. Okay, so that means as the 50, as when the K equal to 50 here, and when the system get a settling status, that means if you have the step response here, the step response equal to 1. If your system got a 1 watt difference, ultimately your system will get a 50 centigrade. And take care here, the 1 watt, this is the input of this transfer function model. Okay, so if we think about here, consider our initial status equal to 1 watt. That means if we give a system to 2 watts, that means the difference of the input equal to 1 watt, right? 1 watt. So the difference of the output will be here the K, the 50 centigrade. And then we also need to involve the initial status 50. So finally, the temperature of this system will be equal to 50 plus 50. First 50 came from the initial status. Second 50 come from here. Okay, so that equal to 100. This is how this calculation behind. And take care here. So the 1 watts came from the delta input, the change of the input. When we apply 2 watts, okay, so the initial status was 1 watt. The difference of the system will be 1 watt, 2 minus 1 watts here. Okay, back to the question. If the input of the system is a 3 watt, so the model input will be 3 minus 1, 2 watts. Then the final output of the model, this is 2 multiply 50 is 100 Celsius degree. Then the final of the system is 100 plus 50 is 150 degree output. All right, now I will use this equation, this transfer function. And firstly, let me show if we program this into the MATLAB, how the step response will be in the MATLAB. Okay, so this is the MATLAB. So firstly, we define K equal to 50. And the exponential frequency A equal to 0.1. And my system, the transfer function, equal to K, nominator equal to K multiply A, and the denominator S and A. Okay, so let's see, the transfer function will be, okay, that equal to S plus 0.1. 0.1 is exponential frequency. And the nominator equal to K multiply A, right? That equal to 5. This is my transfer function, okay? And then we can get a step response of my system. This is my step. Alright, this is the heater system step response. And according to the transfer function knowledge, we can calculate the 63% of this 50. So 50 multiply 0.63, that equal to 31.5. So let's verify this step response time. So we can try to get this 31.5. So we can see while the system experienced 10 seconds, then we got this 31.5, the 63% of this difference change, the step response difference change. So if you recall, when this time is equal to 10, so the A is equal to 1 over T. T, it did 10 seconds. So this A equal to 0.1. This is our transfer function here. The A is equal to 0.1. K equal to 50 here. Okay, here we can use this curve to verify the response of our PLC result. Okay, so when we give the step response of equation after we programmed into the PLC, and let's see if the output of the equation can react as this way. And for example, when the time got 40 seconds, so this result, if it can get this temperature, almost get this 42 degree. Okay, so we can verify the result. All right, this page has too many things here, so I will reorganize this page. Again, this is the original transfer function, and in this case, A is equal to 0.1, K is equal to 50, and the sample time, I will use the 200 milliseconds as an example, and I will use Siemens PLC using TI Portal as my programming platform. Again, it doesn't quite matter which kind of brand of PLC you are using. Basically, once you know how we can program this equation, you can use any PLC, any hardware platform, embedded system, code system, or even computer system. You can implement this difference equation. So let's shift to the TI Portal. Okay, in this case, I'm using 1200 PLC. Okay, so firstly, I will create a function. So the function, I will run the equation, the first order difference equation. So here I can name this is my FC first order difference equation. And my programming language, I will use SCL. In this case, the ladder logic also workable, but SCL, the structured test logic, will be more commonly used for middle and high-end PLC system. So we will firstly program the core of the equation, and when we call this, we have to involve the sample time concept. So I will explain that after. Okay, so this is the core of this equation. According to this equation here, we need to define some important variables. So here I will create a data block here. So I will create DB. So it named DB first order transfer function. Okay, global DB. Okay, once we create this DB, I can declare. So firstly, I can declare the K. Okay, K, this is the real. Okay, and in this equation, I also need the A here. Okay, A is real. Okay, we will retain that. Okay, very important. And then we will create, if we come back, so I will create one variable can store this area. So this expositional area, because once this area got calculated, so we will see this area is sharing use this area. So they are the same, right? So we can create one variable represent this. And then we will also record the previous the output and the previous sample of the input. Okay, so I will create 3 other variables. I will first create the input X, so real, and output Y. Okay, and then we will create one variable to store the input and output from the previous sample. Okay, so this is the x k minus 1. Okay, and the output k minus 1 will use to store the input and output from the previous sample. Okay, then we will create another variable to store the expositional area, the expositional factor. Okay, so we'll create this. Then let's go to the FC and let's program this. So according to this equation here, we can firstly define the k. This k is equal to 50. And the A expositional is equal to 0.1. Okay. This is the temperature system, so I can name this here. Temperature system. And then we will calculate the expositional factor. And the expositional factor is equal to the expositional, and we also need a value here, and we also need a T sample. Okay. And to calculate this area, we will need the A and the TS, the sample time. So the sample time I will define as the 0.2. So I will create another variables. Okay. So here, create another variable that means TS. Okay. TS here. And the TS, we will define the TS, so equal to, in this case, I will use 200 milliseconds. So here, the unit is the seconds. So I will define as 0.2. So here, right, sample time is 200 milliseconds. Okay, here. And then we can calculate this expositional factor. Okay, so this expositional factor here is equal to exp. Okay, and the power area is equal to minus. So A, right? This A here, A multiply the TS. So the TS is this. Okay. This is the expositional factor, how to calculate this. So if you are using the ladder logic, you can find this command from the math function, and you will see the exp. Okay, the expositional calculation here, expositional value. Okay, exp. And basically this is a very common instruction. Okay, then once we got this, the equation will be very easy. So according to the equation at the right top corner, so the y output, yep, is equal to this area, right? This area expositional factor multiply the y came from the previous sample. So this is this. So we can drag to here. Came from the previous sample here. And then plus. So I will use another line here. And there's one bracket. 1 minus this expositional factor here. And then multiply the input from the previous sample right here. Okay, and then multiply the k. Okay, multiply the k. So this is the equation. Okay, so this equation comes from the two area, the first area and the second area. So if you compare this difference equation from the original equation we derived, we will see they are the same. Okay, then the final things, we will figure out the previous sample of the input and output. After, below this equation, so the input from the previous sample, we will grab the input of x, transfer to the previous sample. This is the beauty of using the computer system. So the previous sample, the only thing is you just transfer that below this calculation, right? Then when the next time this program got called, then the x k1 here, though the value of this variable came from the previous call, right? Previous time, right? Same thing, the y k minus 1 will came from the output. Output here is based on the calculated, right? So after we calculate it, we will record here, prepare for the next time. Okay, keep in mind here. And then the input of this system is here. We give the input, in this case, this input, the input voltage. In this case, the input unit is voltage. Is voltage. And the output unit is Celsius degree. Okay, Celsius degree. That's it. So you can see after we convert to the difference equation, this is the core of that equation. It's very brief, very simple. And then the final thing, and very important, is to call this FC. And when we call this FC, we can now use the OB1, because OB1, that main program is variant, because to calculate this difference equation, it has to use the solid sampling time call, 0.2, 200 milliseconds. Okay, if your call is 100 milliseconds, then you can change this TS to 0.1. Okay, so in this case, because I define as 200 milliseconds call, so I will create a cyclic OB, cyclic interrupt OB, and I can define as 200 milliseconds this cyclic time. Okay, I can select as the ladder logic. This cyclic time here must match with your program setting here. Okay, so it named OB30, and then I will call this function. I will drag to here. Okay, once we drag here, once we start the CPU, so this OB30 every 200 milliseconds, it will run one time. And then this equation will be calculated one time. And then based on this 0.2 TS sample time, so this equation will calculate one result every 200 milliseconds. Okay? All right, and now we can download the program. Once we download the program, start up the CPU, so this cyclic will automatically run, then this equation will keep running. And to view the results, we can firstly create a watch table here. So we can drag this inputs and output. Okay. In the meantime, we can add a trace, but I will firstly download the program. Let's deliver an input. For example, a step response, 1 watt. And let's see the output. As I calculated in the beginning of the video, so the output should equal to 50 degree. Okay, so if I compile and download. Okay, download the CPU, download the program. Okay, now if I go online, start monitoring. Now in the initial status, all the input and output, they are 0. So if now I give a step response bump test, deliver a 1, we will see the response of this output. So let's give a 1. So we'll see this will react as a temperature. It's going up, it's running an explosional behavior. In the meantime, if we go into the FC1 and we go online, we'll see this is the calculation result. So K is equal to 50, and this explosional factor here is equal to 0.98. Okay, and the output here is keeping running. And if you recall, after 10 seconds, so the temperature will equal to 31.5 Celsius. But basically, after 1 minute, then the temperature will almost equal to 50. So we will see after for a while, after 1 minute, so the temperature will close to the 50. Okay, very close. That means this equation is working here. Then to see this more clearly, I will set up a trend. Okay, we will use the trace function from this PLC, and we can see the response. And then we can compare with the MATLAB. Okay, so meantime, I will set a 0. Let it go back to 0. So transfer, then the temperature will decrease. Okay, and then I will set up the trace so we can see the trend of the output. And let's click this add a new trace. And here we can select the output Y here. So we can drag this tag to here. Okay. And the sampling time. So we can select, so we can leave as a default. So because this is a trend, to correlate it with this cyclic interrupt, so we can select the OB30, 200 milliseconds sample time to show this trend. Okay, 200 milliseconds. And we can pick 200 samples that can leave this entire trend. The duration could be 400 seconds. That's good enough, right? And trigger, we do not need that because once we click on, we can give a step response. Okay, so now we can download this configuration and then we can shift to the trend. Okay, let's start this recording. Okay, it started recording, and in the meantime, let's open this watch table. And now I return to 0. Now I can give a 1.0 and let's start. After we triggered, it start ramping up. And this curve shows exponential curve. Okay. It start at this 16 here. Okay, so it's approaching 50. We can wait for longer. So basically wait till more than 1 minute. Okay, so basically we can see the result approaching to 50 now. Okay. And we can stop this recording. Now we can do a comparison with the MATLAB. All right, I reorganized my window so we can compare them side by side. So we can find when the output value got this 31.5, so how long it reached there. And we can also verify, so when the value got this 41.5, so how much times it took. So we can firstly find out the 31.5 spot. So 31.5, we can click this. Okay, so we started from here, from this 0, okay? And let's firstly find out the 31.5, yeah, roughly here. And we can see the time. So and we can see, and as we can see, this delta time is almost the 10 seconds. Okay, so as we can see, when the value got this 63% of this final 50 Celsius degree, so it was using 0.16 minute here. Take care, this is the minute unit. So it's actually 10 seconds. So if we zoom in, we can see this is the 10 seconds. And we can compare here, so the spot here and the shape, they are very similar here. And if we zoom in, we can see this value will be changed to 10 seconds. When this unit change to second, okay, we can see the delta t between this gap. This is 10 seconds. Okay, they are the same. Then let's find out the next spot. The next spot, let's find out this amplitude 49.2, and let's compare if the time equal to 41.5. Okay, so let's go to the amplitude 49.2. 49.2. Okay, so then this is the delta time. Then if we zoom in, when the time changed to second, okay, it changed to second here, and then we can see the duration time. We can compare. So the duration time was 41.5. So in MATLAB, a result 41.5. So in MATLAB, while we are doing this step response, this is the time response based on the transfer function. And the left side, this is by the difference equation by the PLC, while this equation is calculated by the 200 millisecond time, 200 millisecond sample time. That means this difference equation is almost the same as this transfer function and this time response. That means from the video 1 to this video, we convert the original transfer function to the ice domain and then convert to the difference equation, and then we program into the PLC all those procedure steps we implement correctly. Now, all the tests were based on the initial status equal to 0. But if you recall, in our example, while I'm doing this transfer function, this temperature system, that initial status wasn't be 0. If you recall this example, so the moment when I was using this example, this transfer function, that initial status, the input was 1 volt and the output was 50. And considering this video has been 30 minutes, it's too long. So I will use the next video to discuss this initial status, how we can program this situation. See you in next video. Thank you for watching. If you like this video, please give me a thumb up. If you like to watch more videos in my channel, please subscribe and hit the bell. Thank you for watching.